props to the UK Met Office for being able to tell me if I get, no second. Gracias. So good for them for telling me if I get 12 minutes basically of rainfall rates within half pass. So that's really nice. But before that, so I'm originally from Boulder, Colorado. I grew up in a really mountainous area and I find diverse topography quite interesting. You see my hometown at the top right. And I grew up under water restrictions a lot. So we have a ton of water scarcity issues, and that's always been something that's been really interesting to me. And then after I did my undergraduate degree in physics and political science, I decided to go work in science policy. So I worked in DC for a couple of years before I came to grad school. And basically what we have at the national policy level in the States, we have a national science advisor, and their team is the Office of Science and Technology Policy at the White House. And then in the 1990s, Congress set up a really small organization called the Science and Technology Policy Institute, where I worked, which basically does in-house research and development for this Office of Science and Technology Policy. And when you work there, you don't really get to choose what portfolios you work on, but I was assigned primarily space weather preparedness. So looking at weather patterns in the sun and how that can affect our critical infrastructure services. And then I did a lot with space nuclear power and propulsion. And primarily while I worked there, we were redoing the launch regulation guidelines for any type of rocket into space and it's carrying a nuclear payload. Essentially the risks really change. And so you need to relook at the models. And these are really important for deep space missions when you're too far from the sun to use solar power, and near solar missions when the sun will literally just melt your solar panels. But so this is different from what I do today, but I really enjoyed being in the space between modelers and decision makers and figuring out how can we kind of improve our decision making, giving an imperfect informational environment and think about risks. And so, no second. Okay, this works. So again, what I talk about today is primarily focusing on dynamic ensembles and focusing on seasonal forecasts of rainfall over Central America. So basically, using models again and thinking about how well do they perform and can we make them better. And essentially, when you're going to make forecasts, you have three general approaches. You have statistical methods where you're relating observations to identify patterns to make a prediction. You have dynamic approaches, which is primarily what I evaluate when you focus on physically based Earth system models. And you've basically constructed a fake version of the Earth and you run simulations. And you might have an ocean model, an atmospheric model, maybe some Arctic sea ice. You throw a whole bunch of things together and then you run simulations. And then you have hybrid approaches, which kind of combine a bit of both. And so in my first two papers, I will give you a summary of kind of what I did in the beginning of the PhD, where I was evaluating the status quo of how these models perform over Central America. And then I'd love to share with you some of my current work, where I'm really focusing on improving some of these forecasts, and I'd love to get your feedback on how I can improve it. So before we dive in, I just wanted to show you a map of where these centers are based, where these models come from. Because as you might notice, you'll see that primarily you have over North America. These are all contributing members to the North American multi-model ensemble, which is one of the main ones. And then you also have a bunch in Europe, which are primarily contributing to C3S, which is the European system for having an ensemble. And one thing you might notice right off is all of these ensembles are based in the north over large centers of mass. And a lot of the research there focusing on kind of targeting these forecast development is considering those kind of conditions. And it's not focused on the tropics, it's not focused on places that may be more dominated, by the oceans for their rainfall. And so I thought it would be super interesting to evaluate Central America, especially since you have a really thin isthmus, you're between two big oceans in the tropics that have different circulation patterns, and you have really varied topography as well, which is really challenging for these systems. So before I kind of start just to give you a summary of what I've been doing in terms of these evaluations, I just wanted to go over three terms that are really important, which are just models, which I just discussed, which are the structure for each of these different services, essentially have a different version of how the system works. They might not be that different from each other, but they do have their own models. And then you have members. So each model will have a certain numbers of members within it. So when we run one of these forecasts, you initialize it, which basically means you feed some observations on April 1st, if you want to make a forecast for May, let's say, and then you run the forecast to give you a prediction. But one of the challenges is, which I'm sure you all know, is that we have a very imperfect understanding of what the world looks like. We don't have a perfect version of the observations. So one of the ways the model is going to run this is they perturb their forecasts and they make a few different guesses of what the observational state is, and they call these numbers. And you can within these models have maybe 4 guesses of what the Earth system looks like today, up to 51 guesses of what the Earth system looks like today, and then run all these simulations, and you can either get a probabilistic forecast at the end with all the members, or you'll have a deterministic forecast if you collapse into the mean. And then the final term that gets mentioned a lot is ensemble, and that's just when you're grouping these models together into large groups. So you have the contributing models to the North American multimodal ensemble, the contributing models to the European C3S system work. So just to start, I wanted to give you a brief overview of the first paper when I was teaching myself how to do one of these evaluations. I got to work with Mr. Merkel on this, and so then we started collaborating together, which was really fun. But I decided to just take one model, C5 from the European Center from Medium Range Weather Forecast, and the latest update, and really focus on how does this do over the dry season, thinking about normal rainfall variability and low rainfall extremes especially. And I did a statistical approach, which is pretty traditional for these types of evaluations, where I just look at the hindcast, so these reforecasts over historical years. The available time period was 1982 to 2016. I took it over a variety of lead times and looked at different months using the model mean and 25 model members that are available for reforecast periods. I'm not spending too much time on this paper because it's kind of like a simple first start to say like how do you do the model. But I just wanted to show you one of the thoughts that came out of this, which is looking at the spatial variability of the skill over the different months and across lead times. So you have lead times going across the top, 1 to 6, up to 7 months out. Then these are just some key wet season months that I've zoomed into, focusing on the continuous rain probability skill score. That's just looking at a more probabilistic skill metric. But I just want to point out to you, like, it's a good gut sense here, like in July and August, that midsummer dry period, the model can definitely capture that pretty well. It's a really consistent phenomenon. But when you get into more, variable rainfall periods, especially in that early wet season period and that late wet season period, there's a lot more spatial variability. Maybe in October, also a bit better than that 1 month lead time, but you have zones where across the lead times, the model's always really pretty good. For this paper, I ran like a very simple linear regression against the spatial skill, just using like elevation and continentality, which is different from coast. And I think the R-squared value is like about 3 at the most. So it's like not really representing all of the difference in spatial skill, but it's part of the picture. Another thing that I did with this paper is I just wanted to look at some performance during some historical drought periods. And so there's this really nice review by Oscar Collins in 2018 that focused on historical drought impacts to the agricultural sector over the dry quarter. And so I just pulled a few of the droughts events and looked at model performance, basically thinking about the biases in different phases of ENSO, because I just wanted to start getting a peek at kind of, are there different phases of ENSO in which the model is better, ones that are doing well in these historic periods. And I mean, basically I found like lower is better here and higher is worse when you look at the skill measure, but you do see a lot of variability. It's not one phase of ENSO is also necessarily a better time to use this model than not. But the other piece that I wanted, the reason I included this figure in the first paper was one of the things I'm doing here is I'm just documenting when periods are actually occurring between these dashed lines of rainfall anomalies below -1. And you'll see across all these drought impact events that were documented, you're not always getting really intense rainfall anomalies. And I think it's important to just kind of emphasize that rainfall matters and rainfall forecasting matters for drought preparedness. But again, it's not the whole picture. You have socioeconomic conditions, you have all these other factors in the physical climate that will affect your drought impacts. And so, improving preparedness looking at rainfall forecasting alone is not, going to give you the full resilience picture. So then for my second paper, I really started expanding my analysis and getting more operationally driven. So I started working with Garcia Lopez a bit at INSIGUME and the National Weather Service for Guatemala. And they're really working on the contribution to the Central American Climate Outlook Forum and their rainfall outlooks that happen a few times a year. And let's grab some water. Okay, so basically, we were focused a lot more on kind of an operational approach. And what we were really curious about was how do you actually compare these models against each other? Are there any real differences? And that was kind of question one that Alan was really interested in. And then what I was really interested in was how do forecast types actually affect the final outcome, the output as well. So you have your direct rainfall forecasts when you're taking the outputs of these models, but then you also can start generating some hybrid forecasts. So there's this tension between the models are really good at sea surface temperature predictions because sea surface temperature changes so much more slowly than rainfall, but rainfall is not driven by sea surface temperature alone. So when you kind of lose that piece of the puzzle and only predict sea surface temperature and then statistically relate that to rainfall, can you improve upon the forecast? So this is where I'm getting some hybrid forecasts, focusing on predictions over the tropical North Atlantic and in the 3.4 region. And then finally, another thing that I was focused on was really baselining these ensembles against some more informative statistical approaches than, let's say, a climatology, where you're taking the mean across several years, or a random forecast, because that's not really operationally done very much. So what I instead did is I created some basic statistical forecasts using 3.4 to do an ENSO statistical forecast, and over the tropical North Atlantic to say, if I made some really simple statistical forecasts, do they ever outperform my fancy dynamic models that supposedly have more information? And where's the comparative value, essentially, of using the dynamic approaches versus the statistical approaches? And when I kind of show you my result, I kind of divided the region. I mean, it's very loose categories, but essentially what I was thinking about was kind of getting a Northern Pacific zone, a Northern Caribbean zone, a Southern Caribbean zone, a Southern Pacific zone, and just dividing it around where that Caribbean low-level jet branches, around the 10-degree north latitude line. And then I also completed the Central American dry quarter in that Northern Pacific zone. So it's kind of like a loose grouping of categories when I'm thinking about different regional comparisons, but I also did some spatial analysis as well across the dry quarter. So this is just, I'm not going to spend too much time on this. It's like, just if we need to go back to like, what models was I using? What forecast types was I using? But the focus right now is shifting from a monthly forecast to a seasonal forecast. So now I'm doing an initialization 1 month prior to a season. So if I take a May, June, July forecast, now I'm initializing in April, and I'm combining a 1 month lead time for May, a 2 month lead time for June, and a 3 month lead time for July, which is what they're producing at the Central American Climate Outlook. And then my metrics are also really starting to shift here. So I have a discrimination score where I'm discriminating between above normal, normal, and below normal rainfall using the 2 alternative force choice metric, and then a detection score. So I'm using the high P skill score to say, okay, how often does my forecast get high rainfall extremes and low rainfall extremes correctly? Looking at above the 90th percentile and below the 10th. I have a flow chart of everything I did for this paper, and I'm not going to spend too much time for it, but the one thing I just wanted to remind myself to tell you is, like, in the steps when you're taking a model and then you're finally evaluating it, is that in between there's a calibration step, and I was using canonical correlation analysis in PyCPTV2, which is how they're doing it in INSIGUME to produce these outlooks. And so that's kind of a step in between where you're not just taking the raw forecast at this point, you're doing a calibration step before you do the final evaluation. So let's dive into some results. I think let's start on the left. This is just the spatial skill looking at the direct rainfall forecast over the region, and I grouped it by the contributors to the North American multi-model and the contributors to C3S, the European Seasonal Forecasting System. And each line is going to be a different phase of the wet season. So you have May, June, July, August, and August, September, October, which were three kind of periods that Alan was really interested in learning more about. And what I would say is kind of at first glance, what you see is that there's actually not that much of a difference when you're just looking at it in terms of these different models. When you collapse them to their mean value, structurally, they're not doing enough differently, especially when these solution components, to really create a difference in terms of the final forecast. So it doesn't really matter which model you're choosing when it comes to discriminating between above normal and rainfall. Another piece that I just wanted to mention here, so you see that kind of orange spot that keeps appearing over Nicaragua in a lot of these models. So I was talking about this with program reaction the other day, and you can correct me if I restate this for me, but my initial hypothesis is I have the models for continually getting the Caribbean low-level jet lag as it branches up the incident. But she was actually telling me that it's probably more of a land use issue. So like the forests are changing so much. We have deforestation happening, we have all these land use changes happening over Nicaragua, and the models are too forced to really pick this up. And it's kind of a good reminder of, you know, how land use and how humans changing the environment can actually be really quite difficult with some of these models. And then that might also affect the forecasts and the final output. Moving over to the right, so now we've collapsed the models into ensemble means. So C3S will be a mean across all of these models, and then mean will be a mean across all of those at the top. Then the joint is all of the models together. And I think when you start seeing the differences between forecasting types, you have your direct rainfall forecasts, your hybrid forecasts coming from the tropical North Atlantic, and then hybrid coming from the year 3.4. And I think just really interesting seasonal differences, like the tropical North Atlantic hybrid is tending to perform a bit better on warm spots in the region in the early wet season, while Nino 3.4 hybrids as this becoming more important and more of a factor later in the wet season is getting better. Except over Guatemala, which I was not quite sure why, over Guatemala, the Nino 3.4 hybrid forecast was performing so well in the early wet season. But now let's get into some kind of like, how do you compare all of these models against each other? So one of the ways I did it is we can start with part B actually. This is just tagging the top performing forecast type across the region in different parts of the West. So I just tagged whether a Nino 3.4 hybrid, you see it's performing really well over Guatemala. That's the number one performer, this kind of like blue-green. In the green zone, it's direct rainfall. And then purple is going to correspond to your hybrid tropical North Atlantic forecast. And so you see over different parts of Central America, different types of forecasts are performing better depending as you shift across the wet season. One of the really interesting things is look at all of these bright spots. So these bright spots get tagged anytime a statistical forecast that I made quite simply outperformed any of the dynamic ensembles. So if I'm just driving into maybe Nino 3.4 or the tropical North Atlantic using very simple statistics, especially as you're moving towards the late wet season, those statistical methods are actually outperforming a lot of these dynamic ensembles. But then my second thought, now we get into this figure up here, was thinking about like, how do we compare these against each other? How do we start thinking about the spread of the ensemble as well, when we're trying to compare them to see are they significantly different from each other? So I grouped these now by taking the spatial average across that Northern Pacific, Northern Caribbean, Southern Pacific, Southern Caribbean zone. And I'm just going to zoom into the North Pacific for now. I'm going to walk you through how I was thinking about this. But basically, each box plot is going to correspond to the spread of the ensemble that was made, so all the contributing models to that ensemble. And then the dot within each box plot is going to correspond to that ensemble mean, if you just take the mean across all of those models. They're color-coded in purple by hybrid tropical North Atlantic, mid blue-green by Nino 3.4 hybrid, and then those bright green and yellows on the left are the direct rainfall forecast, and then you have the middle of the wet season. And these horizontal bars across the top are the scale of my simple statistical forecast. And what's really interesting is I decided to test kind of like how the best ones perform, and I give the stars to the ones that were kind of the best under my criteria using two different kind of reasons for giving them stars. So first, my box plots had to be significantly better using a Wilcoxon-Sign rank test than every single of those horizontal bars, the statistical models. And then the second criteria, it would then lose a star if one of the box plots was significantly beating one of the other box plots. So you'll see, like, there's a North American multi-model box plot that is kind of better than the statistical lines, but it lost a priority because two of the other ensembles significantly better than that. But I think the thing I want to point out is the stars are being given to these ensembles primarily in the early to middle wet season, and they almost never occur across all 4 regions in the late wet season. So even when the ensembles are performing better, they're comparatively better more in this early wet season period rather than the late wet season when the simple statistical models are basically, especially using Nino 3.4, are already doing so much better that the comparative added value of these dynamic ensembles is less. I did the same analysis for extremes. So I was really interested in detection rate of, you've got your low rainfall extremes and then high rainfall extremes on the bottom. And I'm just going to focus on the direct forecast here on kind of these left boxes. But what I wanted to, man, I'm going too fast. Too excited. Okay, so basically what I wanted to show you here is rainfall detection below the 10th percentile over that kind of Pacific zone in the early to middle wet season, to those top 2 rows, is actually quite blue. So the ensembles are actually doing all right with detection of low rainfall anomalies over the Central American dry quarter in many locations in the early to middle wet season. When you're looking at high rainfall extremes, this is also the case. So early to middle wet season, if you're worried about high rainfall extremes, the ensemble tends to do all right, especially over this kind of Pacific zone getting into that Central American dry quarter. But once you get to the late wet season, here and here, the skill is way, way lower. And one of that is, especially if you're trying to think about maybe high rainfall extremes detection, you know, thinking about like tropical storms and all of these issues that are happening kind of later wet season, when you're worried about detection, this kind of approach isn't going to help you very much. The skill is quite low. So there's kind of too much chaos happening over the Atlantic, and it really kind of messes with these ensembles. I want to get into my current research now, so I don't want to spend too much time on this. But the one thing that I wanted to comment on when you're doing a comparative analysis, now focusing on extremes, the spread of these box plots gets way bigger. So the differences between which model you use, essentially, and how they're performing is going to really increase when you're thinking about detection rate of extremes. So once you move out of kind of normal rainfall discrimination into this extremes detection, you get a lot more variability between the models and how they're performing. But so what am I doing now? So just to recap for you what I've kind of told you so far, I did one kind of simple evaluation of one model C5 over the dry quarter, showed some spatial differences. I did one larger comparative evaluation across a bunch of models coming from 2 ensembles, North America and Europe. But what I haven't really been telling you about is why. And that's a really interesting question that could actually help us get to kind of the bottom of maybe starting to improve some of these seasonal forecasts. So, you know, at the end of the day, I've started really shifting from these typical kind of statistical evaluations to now more hypothesis-based diagnostics. So really thinking about when the models get certain characteristics right, let's say sea surface temperature in important locations, is this actually related to their final rainfall forecast? And can you start thinking about why the models are performing a bit better and why are they performing a bit worse to start thinking about improving your model development? And then there's a second piece. So in the beginning, I was kind of talking to you a bit about models and numbers.
So for this whole analysis so far, I've mostly been focusing on model means. So the only difference is between the structure of what each of these contributing centers is putting in, and then they get collapsed to a mean value. But one of the ways you can potentially improve upon these models is thinking about their members and initialization choices. So each of these models has a different number of random guesses they made about the observational state. And my current hypothesis is if they randomly happen to get better observations right, some of these members, can you potentially select the top performing members and then subsample your ensemble mean at the end? So rather than taking an average mean that has lost a ton of information and gets kind of this average forecast at the end across all these models that has, you know, a mean across maybe 200 members, could I take my top 30 members based on how well they did either sea surface temperature or some other important physical parameters, and then potentially improve on my forecast? So this is kind of the concept I'm mocking up right now. If it doesn't go well, please tell me, because this is kind of how I'm starting to think about it. But essentially, I want to really apply this in real-time operationally. So what I want to do is, let's say we initialize our model on August 1st, and we want to make a September forecast. What we can do is also pull the model's predictions of 0.5 lead time, which is August forecast, and then a 1.5 lead time, which is September forecast. But then what we have access to is the observations just prior to when we initialized. That's our available reference data that we can compare to in real time if we want to make a forecast for September. And so my hypothesis was, okay, maybe sea surface temperature changes slowly enough that the observations from my last 10 days of July, as an example, might be a good enough reference for how well the model is capturing August and September sea surface temperature. And then I can pick my top performing sea surface temperature members and then make a potentially better rainfall forecast. And these are the correlations that I ran just to see if this would even work at all. But basically, these are my end of July sea surface temperatures against my August sea surface temperatures, and my end of July sea surface temperatures against my September sea surface temperatures. And this is just plotted globally over the period. And you can see there's some relationship. I have an R-squared of 0.54 here, I have an R-squared of 0.32 here. But at the end of the day, hopefully we can have a better rainfall forecast. And what I plotted for you here, I was just using 1997 as an example because it's easy to see the anomalies, strong El Nino. But for 1997, when I plot the range of estimates that were coming out across the models, it varies by over 5 standard anomalies. So there's a huge range in what these are forecasting in terms of what the rainfall is going to be. So at the end of the day, hopefully you can improve it by picking the better performers. And so my method for selection right now, I've tried a few different approaches. I'm picking my top performing SST members at 30, my top 30, my top 10 to try different how size is going to affect my ensemble. And then I'm doing it at both lead times. And then I'm also trying out, maybe there's something about members that tend to perform better in August and September. So kind of combining those lead times as a selection criteria. But one thing you're probably wondering now is which sea surface temperatures, especially when you're using this. So I've tried a couple of approaches. First, I did some basic slices. So I just took a huge box of the Pacific, huge box over the Atlantic, my tropical North Atlantic zone, 3.4, and the Caribbean. And then the gradients of sea surface temperature really matter. So back in 2007, Eric Alfaro had a really good paper on saying that, it's not one of these oceans that really matters, it's the difference between the two. And so to start kind of capturing that, one of the first things I did is I just did a huge box over the Pacific and the Atlantic to see how it's capturing kind of both mechanisms. But then what I also did after, this was from talking with Prof. Andrea, so thank you for this, is kind of improving my grading approach, is I took the maximum over some of these grid boxes and then just contracted it from the maximum over some of these grid boxes to kind of start getting a sense of how well is the model capturing these differences between the oceans. And then the last thing that I'm putting around is some fancier clustering approaches. So what if we just forget what we know about sea surface temperature, a priori, and we just use statistical relationships to identify locations of interest? And so I've been using this thing on GitHub, which if anyone's interested in doing spatial correlation maps, SunViber has like a really nice package there on Python. Sorry, I'm like losing my voice again, but on Python. But if you're interested in using it, I highly recommend, and I can point you towards the location. But essentially what this does is you cluster your rainfall data. I took a couple of clusters that kind of map along that Cordillera and include the Central American dry quarter, and then I also clustered it into some finer categories. But then you just take the spatial average and then you run it against your sea surface temperatures. This is rainfall. These are my sea surface temperatures to identify essentially locations of interest. And you can do this using absolute value criterion. You can also do this doing what Sam has developed it's called response guided causal precursor detection. So he's basically using a few different metrics to identify these zones of interest, including how close the points are to each other, in addition to absolute value criterion. And these are just some examples to show you, for some of the clusters, September rainfall, for instance, you get almost nothing, just a couple of spots, maybe in the Pacific and the Atlantic. Then for others, we then really get these huge zones starting to get identified when the Pacific is really dominating. But so let's just look at how it's gone so far. So if you just look at mean squared error field score, I've run this for a bunch of subsamples, a bunch of clusters, but I just want to show you a couple of examples. For regular rainfall, this is my all member ensemble. Blue is better, red is worse. You'll see that once you start subsampling, it starts optimizing for some locations and doing really worse than others. So if I take the gradient across specifically Atlantic, I'm really starting to optimize kind of like over kind of this Central American dry quarter of Costa Rica and over Nicaragua. If I just put my SST over the top of the Atlantic, then I'm really optimizing more over that gradient. And then there's a few other approaches. So this is the whole Pacific. This is Nino 3.4, also at that 1.5 lead time. But what I was really interested in was extremes detection. So when we get into extremes detection, this is an example from May rainfall doing low rainfall detection of extremes. So we're looking at below the 10th percentile now. This is my all-member ensemble. There's almost no scale in a lot of parts of Central America, maybe a bit along that Pacific coast. If I take this as an example, just optimizing for Nino 3.4 SSTs, if I take them at my 1.5 lead time, I actually start optimizing over the Central American dry quarter. But then if I use, where I'm feeling a bit confused here is like SST 1.5 over Nino 3.4 really optimizes over the dry quarter. SST 1.5 just over the Caribbean also kind of started optimizing over the dry quarter. But then if you take your SST at just 0.5 lead time, so you haven't let the model run as long, you get almost no scale. And so lead time as well, in terms of my selection criteria, is really affecting how my final outputs are. And then I just kind of tried one of my random clustering approaches, and it has almost no locations in the world that it's identified, but it's already starting to optimize kind of the Caribbean zone. So I haven't quite understood how that's happening yet. This is the same for high rainfall extremes. So I think the only thing I really want to mention here is that these are two gradients that I tried out that are really starting to optimize kind of more over the Caribbean side. And these are Pacific clusters. So this is just a huge box over the Pacific that you draw. And this is one of my fancier clusters, which is this cluster here. And these are both at 0.5 lead time. So now I'm just not quite sure, like, is 1.5 better? Is 0.5 better? I haven't quite figured that out. And so this is just to show you an example that I've been testing a ton of different subsamples. This is just kind of like a small minority of them, but I'm trying to rank them as they perform for different criteria. So this is, we just take the locations that occur in that northern Pacific zone, and then we just make a box plot of how the ensemble occurred, was able to perform using detection of, let's just say, low rainfall extremes. I've done this for May. This is May temperature, May precipitation, September temperature, and September precipitation. And then I just ordered my box plots based on how high the median is occurring. So basically left is worse and right is better. And I'm just tagging here where the all member ensemble occurs, just, you know, for myself to see how many subsamples essentially have a higher median, at least where they're occurring in the region. And I also tagged, I color coded my box plots by the region where I'm picking my sea surface temperatures from. So these kind of blue purples are coming from more Atlantic into the Caribbean. This is more kind of Atlantic. We start with Atlantic, and then Caribbean into these gradients is more blue green, and then the really bright green and yellow are Pacific and New. And I guess I thought I'd see a bit more kind of, you know, grouping by the region that I'm selecting by, but I'm still not really seeing like one region is necessarily better than others. I did the same thing. I mean, this is just a Northern Caribbean example. You know, getting subsamples that perform better than others, but I'm not quite sure why yet, why they tend to perform better. And then the last thing I just want to end on is what I'm really moving towards is I've been showing you performance over the whole time period, and it kind of gets averaged out into kind of met. Like 1993 to 2016, the hindcast that I have access to, you know, it's not really capturing this interannual variability. And one of my supervisors hates these figures, so I'm gonna have to update it. But what I did is I did box plots on the left and just picked one subsample in this blue green. This is my all member ensemble box plot, and this is my just one subsample that I chose. And it's plotting how all the members within that ensemble perform. And I was really interested in both spread of the box plot, so how different are the members performing year to year for the spatial correlation over Central America. And then also this kind of, you see this wave happening, this is temperature. So year to year, the whole ensemble is changing in its ability to perform. And so what I want to get more into is kind of the climate mechanisms in the background that are constraining the ensemble's ability to perform, and thinking about windows of opportunity in terms of year to year, when does it make sense to use these ensembles? And then when does it really make sense to kind of just disregard them? So that's my talk. I just wanted to put here, in case anyone's ever interested in coming to Oxford, we would really love to have you. Our funding mechanisms are not always great for PhDs, but there's a lot in place for postdoc options. They have a lot of junior research fellowships that will pay you a full salary. They give you a 3-term contract. They cover all your accommodation. And this is all run through our colleges. So if you ever Google Oxford University funding, it's quite limited, but Oxford College funding is where all the funding comes from. So these are kind of the main colleges that will have a bunch of months to do, and all those deadlines are in January. And then also there's so many research job postings. They're hiring all the time. And so from my department, this is the site where they do all the jobs listings, and those are coming out like bi-weekly on these huge projects if you want to do like research assistantships or associates, and they do host a lot of fellows as well. So yeah, happy to get into questions, and thank you so much for listening. Cool.
Thanks very much for the great order. Sehr geehrtes
me pregunto si puedes saber un poco más acerca el simple estadística forecast que consistió de una regresión o algo así. La otra pregunta que tengo es si usted conoce el modelo CPT, el principio usado en alguno de estos cálculos. Y bueno, como usted dijo, el contraste entre los océanos es importante, digamos, hace recalcar la señal de eso más. Entonces, no sé si en esos modelos estadísticos se usó el índice 18.4, si usar la diferencia estandarizada de los océanos puede resultar en algo mejor.
Ok, bueno, muchas gracias. Ok, primero voy a volver a solo ok, ¿qué estaba haciendo? Modelos estadísticos muy simples, como una regresión lineal
Pero, okay, ya no sé esta palabra, but it's like cross-validation, like leave one out. So, like 1993 to 2016, and I forecast 1994, that one gets dumped out, and I'm just running the regression over the other years. And it was pretty simple. And that could definitely be improved on. So if even just these simple regressions are working, I'd be curious to think about how fancier ones work. But then also the one thing that might kind of bias the sample that would be interesting to think about is using training data that only happens prior to those forecasts that might be more operationally relevant. So like if I'm forecasting 1994, only running regression 1982 up to 1993 or something. So kind of the next steps I could start playing around with that as well about how I set the training sample. PyCBT. All of this was done in PyCBT, this entire paper, and it's all run through basically the notebook that IRI gives out to a lot of the national weather services. And I also started, through this work, I just called up a bunch of guys at IRI actually. And so now for the current work, we're mostly working together on kind of enhancing some of the subsampling techniques. So basically, it's all done through PyCBT2 and CBT in that notebook. The canonical correlation analysis step, this is all the Simon Mason that IRI developed that for PyCBT. And then what they have, they're coming out with like next gen is how they've termed it for that next gen ensemble approach. But that ensemble is an unweighted mean across all the models. The only thing you pull out of that ensemble is going to be an unweighted mean across all members. And so what I'm playing around with now is like, could there be that one extra step where you get to kind of pick how many members come out of it, maybe based on prior performance. And then the last one, you're talking about gradients, right? Like which is the best location to select from?
You can construct an index based on the difference in the standardized SST from the Pacific in the Caribbean. And so that would usually improve the skill of the seasonal forecast using SST index, not only a medium, but a
and so when I construct that forecast, I mean, I can chat to you more about that because I'd like to do it better, but essentially constructing the index between the two, what locations are you pulling from, essentially?
You can use AMO, right?
AMO is one choice, but you could use tropical North Atlantic, struct, for example, linear treatment for, but the trick here is that you need to standardize the time series of all index before the subtraction of the index. Because variability in both regions are different.
Right.
I think that's the question we will make.
Yeah.
You will normalize the index to construct the gradient.
Okay. I mean, basically, it's all standard. Everything's been standard and normalized, but it's not. I didn't do the index itself, like the gradient. I didn't then go and do a standard anomaly of that gradient. But everything I'm working with is in kind of this anomalized, like I've standardized it across, like it's not like the raw values, if that makes sense, to get out to the interannual variability. I don't know if I've totally understood if I've done the correct step, because I might be missing something in terms of if I construct the index and standardize it. Basically, I converted everything into standardized anomalies before I ran the calculations, but if there's another step, I should definitely like to hear about it.
I have a question. But the first thing is to know the annual cycle of the precipitation, the drivers, the annual cycle. Why is, and I understand that the target is sometimes a city, but why don't you put together, for example, in certain season, July with May, that is part of the Midsummer Road, for example.
Yeah.
With May and June, that is the first peak of the rainy season. For example, in the other target, I think that was June, July, August.
Yeah.
Try to put together June, that is a quite rain values
Right.
in the Pacific Slope. Try to put together June with July and August, that is an increase in the precipitation in the Pacific and an increase of the precipitation in the Caribbean Slope.
So,
When
yeah.
you put that together, I think that what you say is that it is going to get worse and worse. Like this is not because you are putting together two different animals. So
Yeah, I think that's a really good point in terms of kind of conflating, like you're just grouping together parts of the wet season that don't really go together. They have very different characteristics. The reason I chose those was because those are the outlooks that the Climate Outlook Forum is putting out. So I did it exactly how their forecasts are being done. And Alan basically was interested in, he was like, we make a target outlook May, June, July. We make a target outlook August, September, October, and we're interested in getting into a June, July, August rainfall target. And so I said, well, if those are the forecasts that you want to be making, even though they kind of constrain, like they perform really differently across that wet season. I basically just picked it because those were the types of forecasts that they wanted to make. But you're right, like there's so much variability month to month. And so, especially as I'm looking at drivers now and subsampling, I'm going completely back to the monthly scale to see how it changes, like just, September versus October versus June, because there's so much variability in the wet season.
and the other thing is in the law that we haven't created more yet
Oh, yeah.
is I don't know if that's important or not, but it's a little bit small of the real position.
Of like, so I basically took Hugo's paper from 2015, in the, on the Caribbean low level jet paper, that's branching around the 10-degree north latitude line, to make my divisions between zones. And then when I made this map, I just couldn't really fit the Caribbean low level jet in the right place. Maybe this is a bad map version with like how much the wording was getting and like the arrows. But the reason I made the delineation here was based on like Hugo's 2015 paper essentially, when it actually is at 10 degrees north. But I'm super curious if you think there's like a better way to divide it. These are really loose approximations for like different behaviors. Not.
Okay, the
Yeah.
other thing is that sometimes SST cluster work well, by chance, you expect that to obtain significant correlations, quite far regions, okay? But I think that a statistical relationship is valid also if you can explain it by a conceptual physical model behind.
Yeah.
How do you explain, for example, that kind of remote regions physically to improve, through a real physical relationship, to improve the precipitation forecast or outlook in Central America? How are you explain that?
So this is very much work in progress, and this is a really good point to make that, if I'm randomly making correlations based on places that, kind of like, it might be a spurious correlation essentially, like it's randomly getting associated by that time, and it's not being explained by the real physical drivers. So I think when I do like my final cluster analysis, when I'm using it, I only want to be keeping zones that have a physical explanation that I can understand. It's kind of like my final cluster period. And I want to kind of combine that kind of like empirical approach where I'm deriving like what places are the most highly correlated on the spatial maps. I can just go to them. But then dumping out essentially places that don't really make sense. Like, you'll get random things that come up, and those things can be picked out. This is totally random, probably spurious. And so in the final clustering approach, when I'm identifying locations of interest, really kind of just like mapping both together to have a better physical explanation will be a really good kind of next step. The second idea that I had that I wasn't totally, I'd love to get your thought on whether you think this is a good idea, because I'm not sure whether to think about it. But when I plotted my top performing rainfall members against my worst performing rainfall members, the biggest differences that they have in terms of sea surface temperature aren't usually in the main zones of interest that are the drivers. Their biggest differences actually occur in the Arctic. Some of them get the Arctic way wrong, some of the Arctic get it really right. And so I think the thing I'm not sure about is like, do you just select the main causal drivers that you know are really important for rainfall, or do you look at kind of these second order mechanisms that might be kind of loosely associated with the Earth system model, but when the members get it wrong, it really throws them off. So I'm not sure about whether to explore that.
Looking at the results, it's very difficult to have general conclusion about which method, which result is better. So I don't know how are you going to communicate that, for example, to local authorities, things like that. But the only thing that you could say is that the method that it would be recommended for some location is the one that responds to the forecast skill in that particular region, because statistical, dynamical, and indirect, and things. For example, for a particular location would be better one of them.
Yeah.
But in the other region, another technique is the one that is better than the others. So
Yeah.
if you are in a position of an authority in one country, it's very difficult to choose one first.
Right. Yeah.
How are you going to recommend that? For example, if you are planning to do that, for local authorities, or you are planning?
It really depends on the application. So, I mean, one, I think if we're just looking within an approach, a recommendation that is pretty simple is that if you're using model means, it doesn't really matter which model you're choosing if you're just going to be discriminating between events and using term size. That's just within a forecast type. So in terms of that recommendation, it's kind of like, don't worry too much about which models you're pulling from. It's not going to make a huge difference at the end of the day when you're using model means. Now, when comparing with forecast types, it gets a lot more complicated, and that's where it really depends on the application. So climate outlook forum, when they're looking at a much larger scale, they're making, you know, these big outlooks across the entire region, then it really does, you know, it might be good for them if Guatemala is having a really good hybrid forecast over the early wet season. That's a pretty easy recommendation, I think, to put forward. But when it gets really kind of scattered like that, they're probably going to stay with more of these kind of like direct forecasts. And then it's not really worth the added complexity of saying like, oh, do I use statistical? Do I use hybrid? Do I use direct? So direct is going to be the baseline status quo, I think, for most people in terms of when they generate a forecast. And so the best recommendation out of that is don't worry too much about which models you choose if you're going to be using current day approaches. And then if you want to get into some hybrid forecasts, and you're thinking about a part of the wet season, you know, maybe start thinking about a hybrid in the 3.4 forecast just for some specific applications.
Thank you.
Muchas gracias. Espero por todos todavía entonces tenemos un periodo de tiempo. Entonces, tenemos el estado, el trabajo, cada vez necesitas, estamos subiendo la institución más.
Seguimos afuera, muchas gracias.
Hacia aquí, exacto.